So I'm going to talk to you this morning about how you add a new neuron model to SpiNNaker. And this talk is kind of an amalgamation of two different talks, one that was given by Andrew last year, one that was given by Michael last year, so that's why their names are here. And that's why the slide, that's why you might see that the slides change in kind of character between in the middle. So Michael did a specific example and Andrew did an overview. So I'm basically presenting their work to some extent. So I'll first talk to you about how we view a neuron model in SpiNNaker. So I will load all of it because otherwise you'll get confused. So we see a neuron model as having 5 different components. So a synapse, an input type, the neuron, the model of V, so the membrane model is described by, say, a graph that looks like this, a threshold that you can apply to that neuron model, as shown by the dashed line here, and then what we also call an additional input type, which could influence the behavior of the neuron model and be influenced by the value of V or by the threshold. So this is in an API called New Model Template. We have new model templates available for both Pine 7 and Pine 8. We would recommend that you use the Pine 8 one, but if you're still using Pine 7, you can find the Pine 7 template and we can tell you how to do that. The lab that you're going to do later tells you more about that. There is hardly any difference between the two. The one difference is shown here in the Python code. If you're using Pine 8, you need to specify a model data holder. And the reason you need to do this is basically so that we can support 7 and 8 at the same time. We needed to introduce this extra data holder. So you need to be able to code a new neuron model in both C and Python. So the C code makes the executable file, the executable that's then loaded onto SpiNNaker. The Python code basically configures how this is set up and how it's loaded actually onto the machine itself. Then the C code executable is run on SpiNNaker. So they're separate, but they have to be coordinated. I'll explain that a bit more as we go through the talk. And as Michael was talking about earlier, in all cases, the C code that you'll be writing will be solving the ODE, which describes how the neuron state evolves over time and in response to any input parameters that you might have. And I put this slide in the hope that someone else had had it earlier in the week, but I don't think they have. So basically, this is an overview of all of the code at the moment, and where the neural modeling code actually fits in is in this small blue area here, which is then basically loaded onto each of the cores on each chip. And everything else in there you don't really need to concern yourself with for the purposes of this talk. So first I'll describe what you need to do in C. So I'm showing you that picture again of the different components of the model. So there are basically header files for each of the different components that you might want to add. These are all called from within the neuron code in SpiNNaker, and possibly from the synapses code that's within SpiNNaker as well. So Michael will have mentioned this a little bit earlier as well, but basically the parameters in the state of a neuron at any point in time, so at any time step, they need to be stored in the memory. And for each neuron, the C header is what defines the order and the size of each stored value. And these type, as Michael talked about earlier as well, you can use standard integer, floating point, or fixed point as required. And then we also have a global data structure that services everything. So these are the different structures that you can access. You need to say at the moment in the new model template, you can't actually, there isn't an input type defined in the new model template, but you can define one yourself if you so desire, and we can show you how to do that. But at the moment, we have input types for current and for conductance, and you can use either of those. So, going back to the Izakevich example that Michael was talking about earlier, this is basically how you would define the neuron model structure for in the C code. So you have the eight required parameters there, so the A, B, C, D, which Michael briefly mentioned, the variable state parameters V and U, and then I offset and the current time step. And then, as well, the global data structure is defined within this header file. So, how do you implement a state update? So at each time step, the state of each neuron, it needs to be updated in response to any synaptic input and any inherent dynamics of the model. And as Michael was talking about again, there are many different ways that you can do it, and there will usually be a best approach in terms of accuracy and speed for each different model. And I'm referring to Michael's paper again, which he mentioned before. And the key function in the C code is always this neuron model state update function. The other functions are basically mainly used to support this and allow you to do debugging within the C code. So I'm going to continue the Izakevich example in a bit by describing the key interfaces. So this is just the same thing again, but in pictures, because I like pictures. So your neuron model takes in inputs, and the state update function basically gives you a value for V. The threshold will pass back whether the neuron model is spiked. That's a function that you need to define as well. And then you can get the membrane voltage from that model. So these are, again, just those functions that I just mentioned actually in the code itself in neuronmodel.h. So these are the functions that for each model you will need to be able to define. And just to show you a specific example of what we do in the Izakevich example. So this is on top of what, this is above what Michael was describing earlier. So you'll see that his function, his midpoint function is called here, the one that he was talking about in his earlier talk. And basically you collect the inputs, you feed them into the function, you get the voltage out at the end. And at the bottom here, you're making changes after a spike has occurred, i.e. you're either resetting the voltage or resetting one of the state variables according to the parameters that you've defined. So for each of the different components, you have functions that you can define, functions which you need to define to tell the neuron code what to do. So for example, for the threshold type, you will need to define the threshold type as above threshold function, and this will tell the model what to do when it reaches the threshold. So a specific example again, that here we're defining the structure with, in this case, just one parameter with the value of the threshold that we want to use, and then a function here that just basically compares that value to the current value. And then similarly for other components as well, there are different C functions that you can call to write each of the different components of your neuron model. So for the synapse type, you can get the excitatory and inhibitory inputs. For the input type, you can use convert functions. So it's important to mention here that the function in C in this instance is always called input type convert excitatory input to current or inhibitory input to current, even if you're using a conductance model. The conversion happens, but the functions necessarily have the same name. And again, with the additional input, you can get an input value as a current and then work out whether it is spiked or not. So these are currently what's available in SpiNNaker in the most recent release. So each of these different components is available to you to use at the moment. So if you want to write your own that's not here, you'll have to use the new model template. But if you need to use any of these, then what you basically do is you create a makefile that looks something like this. So what I'm showing highlighted in blue here, are header files for things that are already available in SpiNNaker. And for those ones, you define in the input, in the makefile, the variable source directory points to the SpiNNaker API, which then, from which you can get the components that you require there. The extra source dir variable here, that points to the new model template API. So the things that are highlighted in green may be things that you've written yourself that you can add to this makefile and build a neuron model of the different components in this manner. So if you were to say, look at your C code in an IDE, it might look something like this, where you have each of the different directories for additional input for models for synapse types and threshold types. You'll see as well here that there's a directory for plasticity. I'm not going to talk about plasticity in this particular talk, and we're not going to talk about that in the lab that follows this either, but Oliver's going to talk more about plasticity this afternoon. And you'll also see in here the builds directory, so a build for, in this instance, 5 different models that you could build using the components that you've defined here. And each of those directories has the makefile in it that I described on the previous slide. So, in Python, you have a similar kind of structure. So, within the directory Python models 8 Neuron, you have all of the different components, and then a build directory in which you build your model class for feeding the parameters from the Python code from your Pine model into the C code. And a reminder again that for Pine 8 you need to have a model data loader. So why do we have a Python interface? Well, because we support Pine is the first answer, but also because a lot of the underlying code that partitions the data, that runs different algorithms on the data, is written in Python in the Pacman API, and there needs to be some kind of interface between the Python and the C. So I'm going to describe what you do in Python next. So you basically set up parameters for each of the different components that you're going to put into your model. These parameters can be individual values, they can be arrays, they can be from a random distribution. Once you've set these parameters up, you will need to normalize them by using the call this call here in the init function. I also said at the start that if I'm going too quickly for anybody, this is all explained in the lab manual as well. So if you're not really understanding anything straight away now, it's fine. It will be in the lab manual too. But you can always ask any of us and we'll give you direction on what to do. So in Python, there are different functions which you need to define for your neuron model. The important one here is the get neural parameters function and the get n neural parameters function. So you need to tell it how many neural parameters you have and what those parameters are. And you need to remember that when you define them in C, you define them in a particular order. You need to define them in the same order in the Python code. And you also need to define your state variable at this point as well. So, we saw this slide earlier. This is the data structure for the Izakevich neuron in the C code. And this is what you do. This is what you'll see if you go and look at the Izakevich neuron in the Python code. You will see that, first of all, a data type is defined with each of the different variables in it and their data types. So here we have data type S1615, as Michael was describing it earlier. You define your global type, a global type here as well. Then you build the class for your neuron model. So you feed all of the parameters in and convert them, as I described on a previous slide. Within the class, you can define what we call getters and setters, so you can get each of the parameters, you can set each of the parameters. We define these so that in your Pine script, you can go in and define and set this parameter from your Pine script without having to feed it, without having to change the model. You can define functions like initialize v. Again, this is a Pine related function. I'll come back to this a bit later. These are the as I said before, these are the two important functions in the model class. So get n neural parameters, you need to make sure that that returns the correct number, otherwise the C code will receive the parameters in the wrong order or a different order from what you're expecting. And you need to define all of your parameters in the same order that they were defined in the C code. And you can, and these are passed using the neuron parameter function and the data type that you defined in the global struct earlier. And similarly for global parameters, you can also define, get global parameter types is defined here. You also have a function called get neural parameter types, from which you can get any of the types that you defined earlier if you need them. And on that previous slide, you may have seen that there was an inject items function here. You might not know what that means in Python. I don't know how good you are with your Python. But what this inject function basically does is allow you to put a parameter from the interface, so possibly from a configuration file or something like that, into the arguments of a particular function. And this parameter is in addition to any other parameters that you may have defined already. In common ones that you might put in there are the machine time step or the time CR factor. And then finally, to help with the partitioning of the code, the model, you need to tell it how many cycles you roughly expect your code to be running for. And this helps it, this basically helps the partitioner to put however many neurons need to be on each core. So it doesn't matter if you get this wrong, the partitioner is quite good at working through anything that you might have misunderstood. If you give it a number that's too big, your code will probably run slower because it's expecting it to be big, and so it will put less neurons on each core. And basically, it's the same for each other component that you could think of defining, each of the 5 different components. So for threshold type, again, you define the number of cycles, you tell it how many threshold parameters there are, what the threshold parameters are, what the types are. And this is an example of a threshold model again. So this is the C code that you saw earlier. And all you do in Python is you define a class for the threshold type, you pass the value in through the init. You can define the parameter, you can set the getter and setter, as I said earlier. And then you do the get threshold parameters function, as before. And for each different component, you can do a similar thing. So for input type and for synapse type. You can also define a function in here called get synapse ID by target. So you can define each of your different synapses to have a different ID, and then go and get them using this function here. So the overall Python build looks very similar to the C build, something like that. So once you've defined all your components, you put them together in a class. So if you look in the SpiNNaker code, you'll see that these are called model name base in SpiNNaker. So in this case, the Izukevich Kurex base. So you can define, at this point, you can define default parameters for each of the 8 parameters that you might be passing in. You then pass these through the init, and you define each of the different model components here in this way. So you'll note here that additional input type isn't there. The additional input type is defaults to none, so you don't need to define it. And then you take each of these different components that you define, you pass them into what we call the abstract population vertex, and that basically goes lower and lower down the Python chain and passes these parameters that you define here into the C code. The C code runs and then sends the data back off again to the host. You can define other functions in here, like the maximum number of atoms per core. And this is just another example of the API, but using the new model template this time. So here I've called it my model Kurex base. You'll find this in the new model template API, where anything highlighted in green is a parameter that I've defined myself. Anything highlighted in blue is something that belongs to another component. And then you basically feed each of these different components into the abstract population vertex, and that's all you need to do. Here you'll see that I've actually written additional input equals none, just to make it clear. Then you need to tell it what the name of the model is and the binary that you created using the C code. And then finally, if you're using Pine 8, you also need to do this. You need to add another structure called a data holder. So here I'm showing you the Izukevich data holder from the SpiNNaker API. So basically this holds every single parameter that the model needs to know about, and that's basically all you need to do. So you have what we call non-Pine default parameters, parameters that Pine doesn't need to know about. We have default parameters, which are the ones that Pine's expecting you to use in this particular model. And then all you do is initialize the data holder to hold all of these different parameter values. Then at the end of the class, you say which model this data holder refers to. So, a reminder again of what the structure inside the new model template looks like. And that in Pine8, you need to have data holders. I've repeated that about 4 times now, so you should remember it. So from within your Pine script, you can use all the usual things you expect to be able to use in a Pine script if you've set up the C code in the way that I mentioned earlier. So this initialize V function, so the green thing here is the C code that we set up earlier. If you were going to call it in C, you would call it in this way. If you were going to call it in Pine8, you can use pop.initialize parameter equals whatever. If you're doing it in Pine7, then you need to do the thing that's in commented out at the end there. So you need to do initialize parameter in quotes and then the value. Basically, as long as you've told it that you've created this parameter and you've created a set of function for it, you can then refer to it from your Pine script from the population level. So again, it doesn't matter which of the components you've set it in. If you give it the right name, then it should know to set that parameter to that value. And there are examples of this in the example script, which we'll get you to look at in the lab, which is coming soon. And then you can basically use your model within Pine. So as has been described to you earlier, you can set up populations, and basically all you do is refer to your population here. So you would import it from where it's been defined in the data holder. This is Pine8, Pine7, very similar. And you basically pass in parameters that you can choose the values. So from your script, you can set these values. And there's an example of this in the new model template API. In the examples folder, there's a file called myexample.py. If when you've downloaded the API and installed everything correctly, if you run the example script, you should get some figure which looks something like the figure that's on the right here on this slide. So to summarize, the main place where you define your new neuron model is in the C code where you solve the ODE. You have to make sure that the parameters are correctly passed to it from Python. You do a similar thing for each of the different components in the model. So if there's a particular component function that we've not thought of here, it's not available in a new model template, our advice is to copy code in SpiNNaker and SpiNNaker 8 and edit that code. And to say as well that what I'm working on at the moment is a slight rewrite of what we have at the moment to allow the user to define the actual neuron model state update function in a more independent way than it currently is. Basically, at the moment, it's kind of there's a pretty fixed order in which the functions are called. What we're hoping to allow the user to be able to do is to define this function call order in a way that suits the model that they're attempting to write.